Hi guys. So about 13 years ago, I started a little project called OptaPlanner. At the time, it wasn't really serious, but over the years grew. It became more and more serious. And yeah, right now I'm working on it with a team, and it's used all across the globe, and it's open source, of course. So I'll explain a couple of the use cases about of OptaPlanner. I cannot cover them all, but that's basically this session. So let's get started. So the first use case I want to talk about is the traveling salesman problem and the vehicle routing problem. So about a couple of, like 2 years ago, 3 years ago, there was the story of the ultimate American road trip. So in the newspapers, this is the Washington Post. They claim that a data genius computed the ultimate American road trip, and they also claim that he found the optimal path. So let me just show you what the problem was. He wanted to visit 50 locations, 50 landmarks in the US, or at least it's a hypothetical problem, I guess, such as Mount Rushmore, Liberty Bell, Grand Canyon, and things like that. And he wanted to find what is the shortest time to do that. So how can we do that as quickly as possible, spend as less time as possible actually on the road, so we can spend more time actually watching these things. And this is a solution, not the one from the newspapers, but this is a solution. And it takes 271 hours to complete this solution. You can see over here we go from in New Mexico, the landmark over there, we go to the one in California and so forth, and here we go visit the Grand Canyon, which is over there somewhere. So the question is this optimal? Does everybody in here in the room think this is optimal or not optimal? Can anybody decide whether it's optimal or not optimal? Is this the shortest path you can do? And the answer is no, this is not optimal. And there's one way you can see it. Usually it's very hard to see, but here you can actually see why it's not optimal. It's a little bit after the red dots, but you can actually see two lines crossing. And when you see two lines crossing in a simple traveling salesman problem, you can actually assume that there's probably going to be a shorter path where you just go from this location to that, from this location to that. You'll normally spend less traveling time. So this is the solution from the newspaper. So this was on the Washington Post, was in the New York Times. I've seen it in a Dutch newspaper. This is the ultimate American road trip. And all of these papers actually said it was optimal, although on the original blog of Olsen, who created this trip, he didn't actually use the term that it was optimal. So it is 14% faster than that traditional algorithm I used to generate the first solution. And it's actually quite a smart algorithm that he used. And so 14%, 38 hours driving time less. So that's great. More time you can actually spend doing fun stuff in vacation instead of just driving. But is it optimal? And here you cannot really see it as a human, why it's not optimal or not. But let's take a look. So, small. So if we actually start looking into specific parts of the route, this is the route around Iowa, we can see that he used, he went from Minneapolis from on the top with an S form down there. But if you actually look at this solution, where we do it slightly different, a reverse U apparently, we do it in 1 hour less. So this is of course something I calculated with OptaPlanner, of course, and you see this actually saves an hour of time. Right? So simply by using more advanced algorithms, we find a better solution. Another thing we noticed is that roads are asymmetric, which basically means that if you drive from location A to location B, you don't have the same distance if you drive from B to A. So for example, here I'm driving towards A, I'm driving on the right side of the road. But if I would drive from A back on the same route in the other direction, I would have a problem because the cops would probably stop me for driving in the wrong way on the highway, right? So of course, if I drive in the other direction, it takes much more time because I have to do the whole crossroad thing. So interesting enough, in the data set that he used, he presumed that the routes were symmetric. And so he just read it from A to B and then presumed B to E was the same. So we corrected that and we made sure that all of the solutions you see here are actually using the true asymmetric data. And with the asymmetric calculation, with OptaPlanner you would get this, but if you actually use real data, so with the symmetric data, but if you actually use asymmetric data where you actually look into the actual road distances, turns out that again is an improvement you get. That's another 49 minutes that you save. And more interestingly, OptaPlanner at that point tells you in which direction to drive the route. So it actually tells you, as you can see here, to drive from top to bottom. And that's not really a coincidence, because if you then look at this new route, so this is Olsen's trip, and this is the OptaPlanner trip, which is 2 hours faster, which is about 1% faster. Again, already on a very good algorithm, so 15% in total. And it's also 33 kilometers faster, about 20 miles shorter, right? You notice that it also tells you to drive the route clockwise. Anybody got an idea why it's clockwise? Because it's always better to turn right than it is to turn left. It's always faster, not just on highways, but also on crossroads. So if you ever have to do grocery shopping, you have to go to several stores, drive it clockwise. It's going to save you like 3 seconds or something. So. So what is constraint solving? So constraint solving is solving this problem, so let's take a look. So this is the OptaPlanner examples app. This is in an old school technology swing, but I'll show some in the newer technologies too. And OptaPlanner is just a library below that, so it has no connections whatsoever with the swing stuff. You can see we have many examples ranging from hospital bed planning to planning dinner parties or weddings and flight crew scheduling and stuff like that. Now one of them is the traveling salesman problem. So here this is a crude map of Europe, and we want to go to all of the capitals of Europe. And we want to do that in the shortest path. So if you start solving this, you'll see that here at the bottom, OptaPlanner finds a route and tries to minimize that route. And as you give it more and more time, it finds a shorter and shorter path. And this is actually the optimal path, 216,001. Now, what's quite interesting is what happens when we add a location. So one of the nice things we can do with OptaPlanner is we can add locations in real time. So for example, I can say I'm going to add a location here between Madrid and Lisbon, and just added that. Or I can add a whole bunch here in southern France, right? And he automatically adds those. You can see, by the way, that this is not yet using real roads yet. We'll do that in a minute. This is just a demonstration without. And then but the more interesting part is what happens if I would add a location here where my mouse is right now. So if you add a location here, notice what happens to the upper route. So the upper route goes from Riga to Warsaw to Vilnius. But if you add a location there, you can actually see that it actually puts it in the lower route. And so Warsaw is now no longer between Riga and Warsaw is no longer between those two other cities, right? Yes, whatever they are. My apologies for mispronouncing those names. So this is quite interesting. So here are 3 optimal solutions for the VRP problem for the 3 different data sets. And what happens if we add this extra 1 location? So in the first one, we add an extra location. And what happens is there's not really an effect. We just get this bump there, right? That's the new optimal solution. And if we do that in the second one, what we notice is that there is a side effect. You see the red thing, right? That is the case what we had in Vilnius. We had a side effect on the top right. And the last one is quite interesting because if we add just 1 extra new location, this is the new optimal solution. It is completely different, right? And this is a snowball effect. And this is, of course, just a traveling salesman problem where we're routing 1 vehicle or 1 person, and we have no other constraints than minimizing the distance. And more interestingly, if you try to solve this with, what do you get when you have a difficult problem in computer science? What has your teacher taught you when you were learning programming? Well, you just split it up in smaller pieces, right? So what if we have this traveling salesman problem where we need to find a shorter route between those 68 dots? Right now still just Euclidean distance, so right distances. We split it up in 4 pieces, and we solve those pieces optimally. Let's forget for a second how we solve those optimally, right? We might be able to look at all solutions, but probably not, because the search pace is exponential, which basically means not with the fastest computers or with the entire Amazon cloud. it's probably impossible to solve what maybe from 50 up locations or something like that. If you do it brute force at least. And let's see, we have those optimal solutions. So we paste those optimal solutions together in the best possible way together, post them together. And the question is this result optimal? Is this the optimal solution? And again, very hard for humans to see, but it's not. It's actually, as you can see here, a distance of 30 over a total distance of 700 unoptimal. And you can see the optimal solution is quite different, right? So MapReduce, great algorithm for querying, great algorithm for distributed querying and stuff like that. Terrible algorithm for cases like the TSP and actually all kinds of NP hard cases, which is all the cases, of course, that OptaPlanner is a good fit for. And OptaPlanner is a horrible fit for queries. Actually, simply doesn't work on those. Anyway, so TSP is actually an academic problem, right? Lots of research papers about that. It's been existing since the 50s or 60s, if I recall correctly. It's not really that interesting until you actually make it the vehicle routing problem. Then it becomes interesting. Then it becomes, worth money, worth CO2 emissions. You can reduce your ecological footprint and things like that. So how does this work? Well, we have a depot in the middle, and we need to deliver, in this case, a number of items across the country. So you can see all the dots here are delivery locations, right? And we're sending out 4 trucks, and they will go to all of these locations, deliver what they, for example, restock stores, or maybe their technicians going on the route to install cable at people's homes, or maybe just delivering packages. Maybe it's a form of a post or a DHL or something like that, right? So what kind of constraints do we have to deal with? Well, the first thing is, the major one, where we need multiple vehicles, is the capacity constraint. So you cannot take one vehicle and go to all locations, because in this case, the vehicles can only carry 20 tons, right? And so you have to deliver 10 tons here and 3 tons there, and you cannot deliver all, you cannot use one vehicle to go to all places unless they come back, which basically means you can do it in parallel with multiple vehicles. In the case of technicians, this would be not the capacity, but this would be more like they only have 8 hours, and after 8 hours they have to drive back to the home, of course, and they stop working for that day. You might have things like an expensive delivery that you need a specific vehicle for, like over here, like an armored vehicle. You see this is a bigger vehicle. You might have things like time windows. We need to drive to that location and be there between 8 and 10 a.m. If you arrive too late, then there's nobody going to open the door for us. If you arrive too early, we have to wait and lose a lot of time. There might be locations that are optional to do today. And of course, the biggest, not the biggest one, but the one that after you deal with all the hard constraints, you have a number of these soft constraints. But this one, so the orange one, are soft constraints, is the driver's wage, of course, right? And of course the fuel consumption, right? So by reducing this, we can actually have shorter routes. So where does this happen? Again, supermarkets, restocks, freight transportation, public transportation of buses, taxis, airlines, stuff like that, and technicians on the road. And we've actually done benchmarks. So we've used the academic data sets, and we've compared the traditional algorithms and on a number of these are on the Belgium data sets, and there are 5 of those. They go up to 2,700 deliveries, and this is the difference you get. You get a driving time difference of 15%. So you actually reduce the driving time by 15%. We've seen the same thing with customers and community users in production, anywhere ranging between 15% and 30% of reduction of driving time. Especially when there are more constraints, you get a higher reduction of driving time. This literally saves companies a lot of money, and this also saves a lot of CO2 emissions, so it's good for the planet too, right? So, quick demo of that, and here we go. So this is. So the problem with OptaPlanner was, of course, that we had a hard time demoing it, especially if you show the swing demos, people just run away. So these days we've written something called OptaWeb Vehicle Routing, which basically takes this library, this light embeddable library, puts it into a full-fledged application where we attach a database and so forth. So it becomes basically a reference architecture. It's all open source. You can take the code behind this, adjust it to your needs, of course. And it's still an early stage, so I'm hoping this will work well. But you can see right now we're driving to all of these locations, starting from the depot over here. We're driving to all of these locations, and you can see it takes 17 hours. And if we zoom into, for example, Antwerp, you can actually see we're using real roads, and we're using real road data, of course, to use the travel time. So now I can actually add a location. Voxed was actually a spin-off from Devox. And Devox is always in Kinepolis in Antwerp. All right, so let's add that location. So I've now just added that location. It's over here, right? And you can see OptaPlanner immediately picks that up, right? It's just to show the effect a little bit better. So I'm going to add a location here near Oudenaarde. And when I click there, you can see OptaPlanner picks this up and immediately starts changing the route to find a new optimal solution. So what happens is that these kind of things happen during the night. During the night, we know, for example, during the day, this is the locations that we want to send our technicians or our trucks to. And during the night, we calculate this great big thing. It works perfectly. And of course, in the morning they leave, and 5 minutes after they leave, a new customer calls and says, "Can you pick something up for me too?" And this is actually what we're doing here. A new customer calls, and we can recalculate the route in real time, right? As you can see there. And then now, sometimes you don't want to have a really, really disruptive change like this. So we'll also we have options to say, okay, this part of the route is already fixed because the vehicle's already left or the technician's already left, and then just change maybe what happens in the afternoon. So we have several options how to deal with that, how to reduce the reduction. But we can in real time deal with the fact that the problem changes, that the world changes, right? Okay. So, yeah. So what is a planning problem? A planning problem is where you want, so OptaPlanner doesn't just work on traveling salesman problem, on vehicle routing problems, but on many other kinds of constraint solving problems too. So what is it? What is a planning problem? You want to optimize goals, and you want to do that with limited resources under constraints. So for example, goals are maximize your profit, of course. Most companies like that, if not all. Minimize ecological footprint. Some companies care about that, but it's nice to have a win-win situation, and it's something we really should be doing, I believe. And maximize the happiness of the employees. So basically increase employee retention and increase customer satisfaction, right? So we do this with limited resources, employees, assets, time, budget, and things like that. And we have these constraints. So the constraints are, if you are using an employee has a number of working hours, you know they can only be at one location at the same time. They can only work for 8 hours a day. The same thing with the skills and affinity of the employees. So maybe for the big trucks, you need somebody who's able to drive that and who has the skill to or the license thing to be able to drive the big truck and things like that, right? And of course, logistic conflicts. If a vehicle drives from Brussels to Zurich, it's in Zurich, right? And you cannot have it, the next thing, let it depart from Brussels again. You need to first bring it back to Brussels. And that's just so, here's a couple of the cases. So I've shown you vehicle routing problem earlier, but other kind of cases are, for example, job shop scheduling, where we need to manufacture things like books or tables or cars, and we need to figure out in which order do we do things, which things we can parallelize, and we do that with a limited number of people, right? So when somebody's working on the yellow job, and then that's the only person who can do that. And for example, in this case, we have two people with a hard hat, 2 engineers. And if we don't have 2 engineers, we cannot do these jobs at the same time, right? Equipment scheduling, things like scheduling hospital beds to patients, for example. So this is the night that they arrive, this is the night that they leave. You can see that we assign each bed to each patient. Employee rostering, which I'll talk about in a minute. Another interesting one is on the cloud. When we have multiple servers, we want to make sure that the processes fit together. So a process that uses a lot of CPU, we might actually have another container image on that same machine But if that doesn't use a lot of CPU, but use a lot of RAM, they are a good fit together if the first one doesn't use a lot of RAM. So you can actually optimize your cloud with this too, and then we've been doing that too. So, so what is OptaPlanner? OptaPlanner is the open source implementation that we're using, of course, that we're working on. It's Apache license, so you can do whatever you want with it, or pretty much under the terms of the license, of course. It's in Maven. There's a reference manual, 400 pages now, I think. Many of examples, 25 examples. You've seen them in the beginning. What was it? So over here. This is all just the examples out of the box. And then we have lots of tests and so forth, right? So question I sometimes get, is this AI? Is this artificial intelligence? And it is this machine learning, right? So one thing to understand in the AI scape is that when you want to figure out, what is the, if you want to do a full text search, for example, for the word cat, right? And then you get, of course, that's your input. Your output is this PDF file. It's very different than if you have an image and you want to recognize that that's a dog. That's a different use case, right? And again, another use case is vehicle routing problem, where we have a problem. We have all the constraints, and we want to minimize 15% less driving times. And these are all AI cases, but they're all very, very different. For example, the first one, you should be using the algorithm called the vector space model on, or maybe one of those other algorithms that are good on those cases. The second one, neural nets, that's clear. That's the big hype today, machine learning, neural nets, deep learning neural nets. And then the last one is really a case for constraint solving, right? And people tend to throw that around like it's very easily. I get a little bit of annoyed by that, because you see a lot of research going on right now for people trying to use neural nets to solve vehicle routing problems, for example, and they get an improvement of 1%, right? So they're not even competitive. They're not even nearly competitive, right? And vice versa, if you would try any of the algorithms on recognizing that the middle there is a dog, that's not going to work either. So if you have a screw, use a screwdriver. If you have a nail, please don't use a screwdriver. Use a hammer, right? Use the right tool for the job. Yeah, so a couple of cases there, of course, everybody knows those. So it does fit in the AI, but it's actually, according to the academic categorization at least, OptaPlanner is not machine learning. It is a constraint solver, so it's just another form of AI. Let's talk about employee rostering, and in this case I'm actually going to go through some Java code. So in employee rostering, we have to assign employees to shifts. So here we have a number of employees, 2 nurses, an engineer, and a designer. Usually your skills will be more in line with each other, right? But just for an example case, I've made it like this. So you see a number of shifts here. We have 3 morning shifts here, 2 afternoon shifts. Here we have 3 afternoon shifts and a couple of night shifts and so forth. And you also see how they got assigned. So you see that this nurse is now doing 3 morning shifts and then 2 afternoon shifts, and then she's free. So that are the data. Then of course we have hard constraints. So one of the hard constraints is we can only do 1 shift per day, right? So that means if she does the morning shift, she cannot do another morning shift or an afternoon shift or a night shift. Then we have skill requirements. For example, for this particular shift, we need to assign it to a nurse. And then we have, and this one needs to be assigned to an engineer, so that's skill requirements. And then maybe some contracts, like this one, don't do weekend work, right? So the last one doesn't do weekend work. And then we have soft constraints. A big one there is, and sometimes this isn't just a soft constraints. In some countries, it's a hard constraints. It's called forward rotation, which basically means that between 2 shifts you need 10 hours. So you cannot say I'm going to switch from a number of afternoon shifts to morning shifts immediately, because then the nurse finishes at 10 o'clock and needs to have our next shift at 6 o'clock in the morning. That's only 8 hours in between, not enough time to go home and get some sleep and get some food in her, right? And we might just have only 5 consecutive shift days, and then we need a 48-hour rest period and things like that. And the biggest one, the one that involves most of that's the hardest one. Let's put the most difficult one, because it's a soft constraint, is a day off request. So here, this nurse wants to be free on Friday, right? For whatever reason, for social reasons, whatever the case may be. And we would like to allow her to be free on Friday, but we also want to make sure that there's enough nurses in the hospital, right? So where do we see this? We see this in hospitals, security guard firms, call centers, anybody who's working not 9 to 5, basically. And again, we benchmark this on the academic data sets. This one is actually easier to get a much better score than the traditional algorithms and what humans come up with. And what we actually did is we improved the employee well-being by 53%. So what does it mean? Well, in practice, it means it's 90%, 95% these day off requests. So instead of saying to nurses, you cannot have your, or to other employees, you cannot have your day off requests, we can now say this twice as little, right? So we only have to say it half of the time, which increases employee retention. Yeah. No big gains in millions of dollars here, like in the vehicle routing problem, but you do increase employee happiness big time here. So for all employees that don't work 9 to 5, not just nurses, pilots, transportation, making steel factory things and so forth, right? So let's take a quick demo at our non-swing UI. We also wrote for this because again we had the same problem, people saying that it wasn't that pretty in the swing UI. So here we have a number of, here we have a week, and you can see we have a number of shifts here. So for example, in the anesthetics department, we have Hugh Rai doing the morning shift. Let's take a look, starting at 6 a.m. until 2 p.m. And then Jay Watt is doing the 9 till 5 shift, and then V. Smith is doing the afternoon shift. So we actually have a morning shift, an afternoon shift, and then somebody who does a day shift, which overlaps with both those shifts because we need 2 nurses at that time in the anesthetics department. So here they're all unassigned. So now OptaPlanner's job is to actually assign these. So the first thing to note is that Bat Fox is doing the last night here. So that actually means if you would be scheduling Bat Fox here, is that we would be breaking hard constraints. So that's you will see that OptaPlanner won't do that. So now I'll just schedule it with OptaPlanner. It's going to solve now for 30 seconds. And you see as it's solving, it's going to start showing those results. Actually, OptaPlanner already has the solutions, but we have some the speed in which we send them to the UI. We still need to work on that a little bit in this implementation. But you can see now that here Amy Cole is doing the morning shift. And you can see that, well, now it's already changed to Gusley apparently. And he's finding a better and better solution. You can see the score here. So in the previous example, so here we go, the score is over here. And OptaPlanner, the more time you give it, the better and better score it finds. But of course, after some time, it flattens out and it cannot find a better score anymore, right? Once it's near optimal or optimal. So, okay, so here we have all of the assignments. So let's take a look at the availability roster here. So you can see, for example, that Amy Green did not want to work on Tuesday, so on Thursday, so she has no work on Thursday. You can also see if you look at the assignments between Amy Green here, there's more than 8 hours in between, more than 10 hours in between all assignments. She never has two assignments on the same day. And you can also see, you might say, okay, why is this anesthetics in the undesired thing? Because if we just simply move that to over here, to the Amy Jones thing, who's free on that day, we probably have a better solution, right? Why didn't OptaPlanner do that? And the answer is that if you look at, there are actually things like skills involved. To be able to work in the anesthetics department, you need a certain skill, and Amy Jones simply doesn't have that skill, right? So you can actually go through that with a fine comb, and you'll see that there's always, if you actually move it, that the score actually gets worse instead of improves, right? So how do we code this? If you want to code this in OptaPlanner, how do we code this? Here we go. So the first thing we do is we define a domain, then we define the constraints, and then we solve it, right? So here's a quick overview on what we're going to do. We're going to create a domain, so plain old Java objects, an employee and a shift. We're going to create a score function. You can do that in Java, but you can also do that in the Drools language. I'll show both in this presentation. And based on that, you build a solver factory. And the solver factory is, for people who know JPA, it's like your entity manager factory. You create one of those for your application, and you know, it's thread safe and stuff like that. And anytime you need to solve something, you create a solver, which is that short-lived, well, depending on how long you solve, you can solve for 8 hours, and you know, some of our customers do that because, and our users do that because, yeah, you can stop after 15 minutes with a 15% improvement, but why not spend another 7 hours to get an extra 1% improvement and save a large amounts of money by not having to on your traveling on your vehicle routing problem, for example, right? By just reducing the distance even more. But anyway, so we have that solver, and then you have that problem. So here we are sending in a case where we have to assign these shifts. Let's see, we have 8 shifts. One of them requires a nurse. We have 3 nurses, 3 employees, and we have 2 day off requests, right? And we're assigning those, and you give it to the solver. We call the solve problem, and we actually get back the solution. So how does that look in code? So we have our problem, right? This is my domain. So the user defines that this is a roster, right? And you can call that foo, or you can call it whatever you want. You can model that whatever in the way you want, but then of course you have to, I'll show that in a minute, have to add some annotations so OptaPlanner understands it. And then you create your solver factory. You can do that based upon in the solver configuration. You can tweak some of the settings, or you can just leave them as is, right? And then you can create a solver factory, and based on the factory, for every time you want to solve, you create a solver, and you call, this is the big thing, the solve method, right? So we give the problem, which is our problem, right, that we defined, to OptaPlanner. OptaPlanner solves it. We get back another instance of our problem, but then with all of the shifts assigned to employees. So you can actually see that if you then go through the shift list. So again, shift is something that we created, so that the user created. That does not exist in OptaPlanner itself. And you will see that if you then ask the getEmployee method of that shift, right, that this when we originally gave it, that was all null, null, and now it's actually going to be assigned to one of the employees. So how does OptaPlanner know that this shift exists and this getEmployee method, you know, that it needs to set employees and so forth? Well, that's because of through the domain. So this is the domain, right? So we have a shift, which is for a specific spot, which requires a specific skill. We have an employee who has one or multiple skills, or maybe no skills at all. He has, you know, a number of skills. It's a many-to-many relationship between employee and skill. And then we have a time slot, you know, when the shift starts and when the shift ends. And so maybe some employees are unavailable for certain times, right? Now, OptaPlanner, what can OptaPlanner change? What can OptaPlanner decide that it will, you know, change mutate your model, to put it like that, right? There's only one thing, and that's the relationship from shift to employee. So we annotate that with a planning variable annotation. So OptaPlanner will change for each shift the employee, and of course they will all start out as null, right? And then of course the shift, which is the class that contains that, needs to have a planning entity annotation. That's just a way to say, okay, in this class there's somewhere a planning variable annotation. Right? So let's take a look. So the spot, plain old Java, has a name, has maybe a required skill, you know, nothing special. You use your plain old Java codes. You can add JPA annotations or whatever you want on these. That's all fine. Your employee, again, plain old Java code, has a name, has a skill. But more interestingly, we have a skill list here, of course, and that's something we'll reuse in the constraints later. You know, so we can put in whatever Java code we want there, but we're going to reuse that later. You know, it's nice to be able to reuse methods, right? And then the shift. Here's where we get a little bit of where we see what OptaPlanner needs to know, right? So OptaPlanner needs to know that this is a planning entity. That means that it contains something that can change. It cannot change the spot of a shift. It cannot change the time slot of a shift, and not at least in this case. That's fixed in advance. There might be cases where it might be able to change that too, and we can deal with that, but not in this case. And then the thing that changes is the employee. So that's a planning variable that changes during the solve, right? And in the tree, what's missing here is actually the definition of where it actually gets the list of employees it can put in there, but I've not shown that here. So so plain old Java class. Again, you can add entity annotations on that from JPA and so forth. That's why we call it at planning entity and not just at entity, to make it easier. And that's how you do your model. Okay. So, score comparison. So, okay, you have your model. So OptaPlanner can figure out, okay, I'm going to put this employee in there and that employee in there in that shift. But which one is actually, you know, how can OptaPlanner know that what do you want? You know, what are your constraints? Well, when OptaPlanner looks at two solutions, it's going to figure out what is the best solution by looking at the score of each solution, right? So let's see how that works. So here we have a problem. Again, those 8 shifts, 2 day off requests, 3 employees. So this is the first solution, right? The first solution, you can see we've assigned the first nurse with 2 morning shifts and the engineer with 2 afternoon shifts. You can also see we've taken this morning shift, which requires an engineer, and we gave it to the nurse, right? That's not good, right? So we have a skill missing constraint. That's a hard constraint. It's red, right? So if you actually tell to the planning people like this is what we're going to do, they will not be happy at all. And the other thing we did is we gave one employee 2 shifts on the same day, also not good, right? And again, it's the same one actually. So this is actually quite a bad solution. So how do we do this? Well, we quantify that. We say there's 2 hard constraints broken, and you can see that right here. So 2 hard constraints broken. Okay. Now, let's take a look at the next solution. In this solution, this is another solution. We don't break any more of the hard constraints. There's no 2 shifts at the same time. The engineering shift is being done by the engineer and so forth. We do break a number of the soft constraints here, like there's less than 10 hours in between here, only 8 hours, and over here the same thing. And here there's a day off request that was denied. We actually forced that employee to come working, even though he or she doesn't want to. So how do we quantify this? Well, we have no hard constraints broken, so we have 0 hard broken. But for every hour in this case I've chosen that we are below the 10-hour marks, I'm going to reduce 1 soft point. So I've actually increased the weight on those constraints a little bit more. And here I've, for every time we do a day off request when we are not able to give that to the person, we lose 1 soft point too. So in total we lose 5 soft points. So given those 2 solutions, how does OptaPlanner know that the second one is better, right? Quite simple. It looks at the score, it looks at the hard score, and it says, okay, the one with the better hard score wins. The one with the higher hard score wins. It doesn't even look at the soft score anymore because the hard score already makes a distinction. So here's the third solution. And in the third solution, we have a day off. We don't have any other soft constraints broken except for the day off request. And that's actually quite logical because we need to assign 2 shifts on that Wednesday. And we have only 1 person that wants to work. So somebody else will have to come to work anyway too, even though they don't want to. So and when we quantify this, this is -1 soft. So given these 3 solutions, which is the best solution? So given these 3 solutions, which is the one we can actually send, which is the one that we want to send to in production? Well, we don't want to send the first one, right? Because they will literally say this is not a solution. This doesn't work, right? And from the other 2, of course, the bottom one is better because it breaks less soft constraints. So again, if the hard constraints is the same, we will look at the soft constraints. So basically, this is the best solution. And of course, OptaPlanner looks at these 3 solutions and says, okay, I'm going to go with the last one. Small note, OptaPlanner doesn't look at 3 solutions. It looks more like 3 billion squared solutions or something like that for a small problem. The search space is huge, right? So it looks at about 10,000 solutions per second, sometimes even 100,000 solutions per second. And for all of those, it calculates the score, and it tries to find the best one, right? So how do we calculate the score? How do we write that in Java or in the Drools DRL language, right? So OptaPlanner has 3 options. You can do it in easy Java, which is very easy. I'll show you. And then we have incremental Java, which is, if you want to go insane, that's the way to go. And then you have the Drools DRL, which is actually like incremental, but a more sane approach. And we're working on a 4th form called Constraint Streams, which I haven't added here yet, which is on top of the rules, but you write it in plain Java with functions and so forth. And then we gave you also an advantage there. So let's take a look at the easy Java implementation. So here's the required skill constraint. So we have one method. It's called the calculate score method, and that has to return a score, right? And we get our roster, right? So we implement this interface, we get our roster, And then we say, okay, we have a score of 0, right? And for every instance that we violate, we're going to increase that score. And you see at the end, we just simply return that score, right? We return a hard soft score where we just take in that hard score, right? So we go through all of the shifts, right? We look at a shift, what is your required skill? So we look at the spot of that shift. We said, okay, what is your required skill? And that is the required skill for that shift. And then if the shift is assigned to an employee, right? So if it's not null, and the employee does not have that skill, so look, there's a not there, of course, right? So and the employee of that shift does not have that required skill, then we're going to reduce the hard score. So that's an easy way to do that in Easy Java. So why don't we just all write Easy Java, its implementations? Why do we have those other options? Why do you have those rules option and so forth? Well, because this is slow. Why is this slow? You might say, oh, because you're not using maps. You're going, well, in this case, you can just go through the shifts once. But there are other use cases where you could use, where you have nested for loops and you can write faster code. But it's not really going to be the big difference, because the real problem is that every time OptaPlanner assigns one of those shifts to another employee, you go through all of your other shifts too. If you have 2,000 shifts to assign, OptaPlanner changes one shift or changes 2 shifts, you're still doing a for loop over all 2,000 loops. While you could do a delta, while you could just calculate the difference with the previous one. This is where the rules comes in. So let me first explain the incremental score calculation a little bit more visually. Here we have a problem, and we can just calculate the score on that. So how many times do we violate the skill required constraint? Well, we see that we violated twice, over here and over here. So these 2 engineering shifts are assigned to a nurse and not assigned to an engineer. And we just calculate them. But we have to, in the for loop, go through all of the shifts and check, do you have your required skills, right? And then we have the sum, and we come up with 2 hard. Okay, that's great. Now, let's presume OptaPlanner will say, let me try taking that shift and giving it to the engineer instead of the second nurse there, right? What is the change on, how does it affect the score, right? Well, let's do it with Easy Java from scratch. So what we're going to do, we're just going to look, this first shift, is it still assigned to a nurse so is it still assigned to a nurse because we need a nurse? And of course it will be, because we haven't touched that shift. So that's actually useless CPU usage, right? Same thing for this one, same thing for this one, and so forth. So which one? So we actually go through all of them again, and we do the whole calculation again, and we recalculate the whole thing from scratch. However, if we do it with incremental Java or with rules, what actually happens is that when we move this, instead of recalculating for everything like we did on the left side, we're now just going to calculate the delta. So first thing we see is, okay, it's no longer on this position, right? So we used to lose a hard constraint there, so we're going to undo that. We're going to undelta. This is the delta. We're going to undo that. So we're going to win 1 plus. So we're going to add +1 here, right? And the other thing, so we take the old score, the score we had from the previous solution. We add +1 hard because we undo that, and then on the new position we check if there it violates any of the skill constraints. Turns out it doesn't, so that's null. So we can just we don't lose a hard score there, right? So the required and the result is the same, of course. We get -1. Of course, if you do it incrementally or you do it from scratch, you'll have the exact same score. The only big difference is that it's much faster, of course, right? And if you look at this from a big O notation for the required skill constraints, it's an order of magnitude faster. So if you have 2,000 shifts, it's 2,000 times faster, right? So that's 200,000%, right? If you see, oh, we have 10% of speed, the ability to do incremental score calculation for constraint solving, like with implementation like OptaPlanner, you need it, right? Especially if you want to scale, and even for medium cases, you need it. It's so important. So one way to implement it is with the DRL. So what you do there is you say, okay, So you can do it. You can do it with incremental Java, but you have to listen to all of the undo and do events, and you have to figure out what the delta is, and you go insane basically. I've written a few, and I've went insane a few times trying to debug them. But we have examples of those if you want to go that path. But the more better approach is, of course, you use the rule language, where you say, okay, we have this required skill. Constraint. And so when we have a shift where the employee is not null, so when the employee is filled in already, right, we're going to check if the employee has the skill of the spot of that shift. So if so that shift's spot required skill is actually in the list of the employee's skill, so the employee has that skill. And if not, we're going to and if that's not the case, then we're going to lower the hard constraint, which basically means we're going to say add hard -1. You can see we still have some, I call it, some extra code there, which we want to get rid of. We want to make this simpler. But this is the base things. And an interesting thing about this is that it will automatically be incremental. Right? So again, here an overview. So we define our domain, we define our score function, we build our solver factory with the build solver method. We create a solver, and then we just solve the problem, giving the input and getting back our output. So you're probably wondering, what if we start doing this? Who's in control? Well, actually, with OptaPlanner, we can do something called pinning. You can say this shift is now pinned, and you can see in the UI we show it with this pin. It basically means that OptaPlanner cannot change that assignment, but does have to take it into account. So he cannot assign Dan Poe in this or that shift, because that's another shift on the same day. And OptaPlanner will work around it. And that's a really great way of convincing people in your production users to say, okay, if you don't trust OptaPlanner, you can always override it, and OptaPlanner will work around you. And in worst case scenario, you can just lock everything, and then OptaPlanner has nothing to do, right? It's a great way to. It's something really useful in case you miss one of the important constraints in the first implementation. So they can actually, when they need an answer right now because that hard constraint is broken, but it's not in your implementation, they can work around it and tell you what the problem is, and then so you can solve it. Okay, we can actually do other kinds of use cases with this. So one of the use cases is conference scheduling, and we actually use this for this schedule, which for Vox Zurich. So Vox Zurich, every talk is assigned with OptaPlanner to room and to a talk, given of course all the constraints that the organizers wanted to put in there and so forth. And how do you notice this? You can notice this because if you see here the big data machine learning talks, there's never two big data and machine learning talks at the same time. There's never two programming languages talks at the same time. There's never two modern web talks at the same time. So we actually made sure, so one of the constraints in there, pretty important one apparently, is to make sure that somebody's coming here and wants to see all of the talks about, let's say, programming languages, can actually do that. There's never two programming languages talks at the same time, right? And there's many other constraints. We use it for DevOps Belgium, we use it for Red Hat Summit and so forth to schedule their conferences. And you can try this yourself if you want to do that. Okay. So how do you get started? You can just go to optaplanner.org. You can press the green button there and you get it download zip, and there you can run the examples to run the swing examples. In the if you follow the source link on the website, you can get these sources for the OptaWeb vehicle routing as well as the OptaWeb employee rostering cases. Okay, and of course you find the whole manual there and all the other things you need. But true programmers, you build from source. So how do you do that? It's quite simple. You git clone it. Of course, you can find again the link on the website. You may even clean install it, no big surprise there, and you can run the examples immediately from the command line if you choose to, or you can also do it from the IDE where you just open the POM file in IntelliJ or whatever the case may be, VS Code or whatever people use these days, and then you can just run the OptaPlanner general OptaPlanner examples app, right? Any questions? And yeah.
Somebody else?
Yes, but go ahead.
No, the other person.
Okay.
For these different use cases, do you have different optimized loaders?
Yeah. So yeah. Yes. So the question is, do you have different optimizers below it? So basically different optimization algorithms. And the answer is yes. So by default, OptaPlanner has, first it runs a constriction heuristic and then a local search algorithm. And it has actually multiple flavors of local search algorithms. So it has taboo search, simulated annealing, hill climbing, late acceptance hill climbing, and so forth. By default, we've configured the one we think works best for most. Actually, we don't think, we actually benchmarked it on all of our different examples and use cases and data sets and so forth. The one that we see that works best on average. But you can actually, so for example, on vehicle routing problem, you can get, with some cases, to 15%. And if you then switch to a better algorithm, you power tweak it, you can get maybe to 16%, right? Or 30% or 31%. And we have, of course, we have something called OptaPlanner benchmark. And OptaPlanner benchmarker, you just give it a bunch of data sets, you give it a bunch of algorithm configurations, or you can just ask, give me the default ones and try all of them, and it will tell you which one is the best one over all of your data sets. And so if you really want to tweak that last 1% out of it, it's really, you can do it that way. And so if you have a small case, it's probably not worth your time, but if you can save 1 million, so yeah, if you can save 1% of driving time, and you're dealing with tens of thousands of vehicles driving around, this literally saves millions. Yeah. Yeah. So my time's up. If any other questions, feel free to ask me after the session. Thanks for listening.